So on today's lesson, we're going to be solving absolute value equations and inequalities. So in all likelihood, when I taught this in our classroom, we split this up into more than one day. So let's first talk about what an absolute value means. So absolute value actually measures the distance from zero. So when you were younger and you learned about the concept of what absolute value bars did to a number, your teacher probably taught you something like makes it positive. But that's not actually what it is. It's measuring distance from zero on a number line. So whether you're at -4 or +4 on a number line, you're going to be a distance of 4 units from the middle point of zero. So the idea was a lot of kids would take the absolute value of -4 and go, okay, the answer is 4. And then when you're smaller, you might have said the absolute value of +4, and then you'd, oops, make it -4. So it doesn't mean the opposite. Doesn't mean make it positive technically, which I know I have written right here. It actually measures the distance from zero. So the idea is when you have algebraic absolute value equations, you don't really know what x represents. So you have to think of it in terms of, okay, the stuff that's on the inside of the absolute value bars, whatever that is, has to be equal to the number 9, technically. But because it's got absolute value bars around it, the inside stuff could be 9 or it could be -9. So what you're going to do when you're solving absolute value equations is once you get the absolute value bars isolated, you're going to set up two equations, one where the inside stuff equals a positive answer, and one where the inside stuff equals the negative version of the answer, or you negate the answer. So if we do a little algebra to solve, get 2x equals 14, so x equals 7 is our first answer. And then our next solution would be 2x equals -4, so x equals -2. And it's not going to kill you or take too much time to actually go back and check your answer into the original problem. If x does equal 7, I plug a 7 in right there, that'd be 14 minus 5, which is 9. Absolute value of 9 is 9, check. And then if I were to plug in a -2 right here, that would be 2 times -2 is -4 minus 5 is -9, and then taking the absolute value of that is also 9. So this was a summative for our class. I might encourage you to go through and check that it is a solution, especially if I maybe gave you one of the special cases we're going to talk about in the next couple minutes. All right, so here, the idea is once the absolute value bars are isolated, which is the first step, to isolate the absolute value bars, and then we're going to set up the two equations. So good news on number one here, it is already isolated, the absolute value bars are. So when I set up my two equations, the first one is just x plus 3 equals 5. The inside stuff equals the answer. Or you could set up x plus 3 instead of equaling 5 could equal -5. And then we solve. So here, subtracting 3 from both sides gives me x equals 2. And then here, subtracting 3 from both sides gives me x equals -8. Again, this is a test to be a great idea to go back and check. Just gonna assume I did it right. So the issue is sometimes kids look at this and go, okay, so what's my right answer? And the issue is that there's more than one right answer. There's actually two answers, two solutions to this equation. So number 2, setting up my two equations because it's already isolated. 7t plus 3 equals 4, and 7t plus 3 equals -4. So solving the first problem and creating the first solution. Let's see, that'd be a 1, and then dividing both sides by 7 would be a 1/7. Here, we get 7t equals -7. Dividing both sides by 7 gives you t equals -1. So the issue is, again, two answers. If this was the test, I would check. Number 3. Notice I have never changed the inside stuff. So I don't ever change whatever's inside the absolute value bars. Speaking of which, number 3, let's set up 1/2 t minus 4 could equal 1, or 1/2 t minus 4 could equal -1. So we're going to solve the first. Add 4. Remember, a quick way to get rid of the 1/2 coefficient is just to simply multiply by the reciprocal of 1/2, which is a 2. Multiplying by 2 on both sides, you get t equals 10. Then on this equation, adding 4 to both sides, get 1/2 t equals 3. and then same math here. That's what I kind of like about these is literally the same algebraic steps that you take is going to be the same. The answers are different because you're going to start with a different solution beginning. All right. So those were all kind of basic because the absolute value bars were isolated before we started the problem. This next set doesn't have that going on. So when I look here at 2/3 is in front of the absolute value bar, a lot of kids think, oh, can I just distribute it into it? You can distribute like a positive answer, positive number, but really, frankly, it's just easier to get rid of it. So if I were to multiply by 3/2 to knock out that 2/3, I actually have the question saying the absolute value of 1 plus 2x is 3. And now I can set up my two equations. So 1 plus 2x could equal 3, or 1 plus 2x could equal negative 3. And then we solve. Aren't you glad that you're a wonderful equation solver at this point? All right, keep solving. And you get two solutions, both of which are correct. X equals 1 and x equals negative 2. Now, this next question has stars next to it, and I think we saw in another lesson that whenever I put stars next to a problem, that means something weird's going on. So it is true that the bars are not isolated yet in this problem, so we are going to have to isolate them. So we're going to subtract 5 from both sides of the equation, and we're going to set up that the absolute value of 2 minus 4x equals negative 2. Now, if you don't recognize that this already is kind of weird, let's pretend that we don't recognize that. Sure, baby. And let's go ahead and set up the two problems. So if I were to set up 2 minus 4x equals negative 2, and 2 minus 4x equals positive 2, I guess, let's look at why this isn't going to work. So we're going to solve, and we're doing our algebraic thing, and we're pretty sure that nothing's wrong in the world, and you get solutions, x equals 1, and like x equals 0. And then, at first glance, you're thinking, so what? Those look good. Those are good answers, right? No, because let's go back to really either one of these lines. If I were to plug in, let's go with x equals 1. Put a 1 right there. So 2 minus 4 times 1 would be 2 minus 4. So it's negative 2. And then absolute value of that is 2. 2 plus 5 is not 3. So that's not working. And if I plug in a 0, 2 minus 0 is 2. Absolute value of 2 plus 5, also not 3. So neither one of these solutions worked, meaning that there is no solution. So that felt like a lot of work for no solution. I think we could have saved ourselves a lot of grief if we just would have stepped back right here. This is stating that the absolute value of something equals negative 2. And didn't we always say the absolute value meant distance from 0, and that's why the answer could never be negative? So why did I do all that work when I already knew there was going to be no solution? Because there's no possible way I could take the absolute value and get a negative 2. So be alert when you're solving these. And if you notice you have one of those special cases pop up, you don't have to go through all the algebra. We are not isolated here. We're going to have to isolate. So let's add. And then divide by 5. You get the absolute value, 2 minus x equals 3. Now we're going to set up, and I don't think we're going to have one of those special cases like we did last time. I think we're good to go. So my two setups are 2 minus x equals 3. I did not change the inside stuff. On this next one, I'm not going to change the inside stuff, but I am going to say it could equal negative 3. So when we solve, let's see, well, don't lose your negative there. Negative x equals 1. So x equals negative 1. And then negative x equals negative 5. So x equals positive 5. And I know you're feeling a little paranoid after that last question, so feel free to plug these in if you'd like, but they work. So those are solving absolute value equations, and equations were nice because you don't have as many rules to follow. You've been solving equations forever. But remember, we just got done solving inequalities, and we realized inequalities are like equations. They have a lot of similar rules, but they have extra bonus rules. So remember, anytime you multiply or divide by a negative, you have to flip your sign around. Something else kind of happens on absolute value inequalities. So they're going to look really comparable to what we just did with the equations, where we set up two of them. So you have to isolate the bars, then you can set up two, and then when you set up the second one, it states that the inside stuff could, it won't equal, but equals, let's say, the negative answer instead of the original answer. So two differences. So the first difference is that when you have your original problem, once it's isolated, if it is a less than problem, so a less than or a less than or equal to, you are looking at an and problem. So I need to call back some old knowledge of and problems. Remember when we graphed and problems back in, oh gosh, what lesson was that? 1.5? Compound and problems? They ended up being like a number and then shading and then another number. So that's what we're going to have today. And then if you have a greater than problem or a greater than or equal to problem, you are looking at what is called an or problem. And then remember from our compound inequality lesson, that was where you had like a number to the left and then a number to the right when you graphed them. So we got to set them up, we got to solve them, we got to graph them, and we have to write the interval. It's going to be good. All right, so this first one here, it was a less than, spoiler alert, it's an and. But if I look down here, this person has already set it up for me. They took the inside stuff and said, just basically they took the bars off. It's less than 11. They wrote down the word and as part of the solution setup. And then the second setup is 2x plus 7 again. But notice they flipped their sign and they negated their answer. So they reversed or flipped the sign and they negated the answer. And that's how you set up the second inequality. Still solve the same though. You gotta love algebra because they just keep building and building and building off of old things. Natalie agrees. So this is going to be part of my solution. I'm going to go ahead and sneak the word and down here because I always forget to write that part. Let's keep solving. Let's see. So x is greater than negative 9. So I am going to graph my solutions that are both and. They're both less than 2 and greater than negative 9. And remember my rule on graphing number lines? I don't really care that you space them out properly. I just care that you put them in the right order. So negative 9 is somewhere down here. I'm going to put a parenthesis opening, so that away, negative 9. And then up here somewhere would be 2. And then graphing all my solutions that are both greater than negative 9 and less than 2 would be all my numbers that are in between here. And then to write the and interval, intervals are always left to right. So this interval goes from negative 9 to 2. I love and intervals because you just pick them up right off the number line. Right, Nat? Totally. All right, so the second one, they already set it up for me because it was already isolated. So the first setup is just to take the bars off. And then the second setup, they flipped the sign around, but they also negated the answer. So now all I have to do is solve. Now, we have a bit of a math battle here because some people will say I need the answer of 10/3 because we're algebra 2 and we like weird fractions. And then some people will say, well, really 3.3 repeating, makes more sense because we're graphing on a number line and numbers to most humans, they work better when they're decimal form. In this case, I don't really care because it didn't specify. So go ahead and put the or right here. And then we're going to solve this one. So 3x is less than or equal to negative 6. And then we're going to divide by 3. A lot of kids think they're supposed to flip the sign here because they're dividing by something negative in their mind. The issue is the coefficient wasn't negative, so there will be no flipping here. So x is less than or equal to, it is flipped from the original problem because that was the setup, to negative 2. So negative 2 would be down yonder. And then 10/3 is somewhere up here. I don't really care where. But this is an or, so remember what that looks like. So graphing everything greater than 10/3 would be like up here. These all both have brackets on them, right? And then less than negative 2 would be that way. with a bracket. And then I'm running out of space. I'm going to have to like write over my face or something. When I go to write the interval here, it starts at negative infinity to negative 2, but then it jumps, remember we use the union symbol, 10/3 to infinity. There's your interval. Okay, so these next 2, 3, 4, whatever, are not going to be set up for you. You're going to have to do this with me. So first thing I notice is the bars are isolated, so check, check. The next part I notice is that it is a greater than symbol. So since it's greater than, we are looking at an OR problem. So when I go to set up my two problems, the first, I just take the bars off, and then I write the word OR in the middle. And my second setup looks the same for the beginning, 4x plus 10, but I need to flip the sign to a less than, and then negate my answer to negative 2. So I'm subtracting. I run out of space. Not bad. So I get x is greater than negative 2, or x is less than negative 3. Now, I kind of spaced it out weird, but if I ever ask you for the inequality solution, this, all of this, including the OR, is my inequality solution. And when I give you a test, it's going to ask you for inequality, graph, and interval, because I'm mean like that. So negative 2, negative 3. I know it sounds like a stupid question, but be careful which one comes first on the number line. That would be the negative 3. And then after it would be negative 2. We're going to be graphing open parentheses on this, and these are ORs, so think about in your head what that should look like. But let's look at the graph itself. Everything greater than negative 2 would be like this, or anything less than negative 3 would be like this, which that is what an OR should look like, so that made sense. So when I pick up that interval and write that graph and I write it as an interval, I get negative infinity to negative 3, jump, and then negative 2 to infinity. Good donut? All right, uh-oh. That one's got stars, so you know something weird's gonna happen. Let's pretend like we don't see stars and that we don't know that something weird is gonna happen. This is set up as an OR. So when I already have them isolated, so I'm gonna set up 2x plus 3 is greater than or equal to, whoops, negative 4. Or 2x plus 3, flip the sign less than or equal to, and then if you negate a negative, now it's positive 4. So I'm going to skip steps a little bit here. I'm going to subtract 3, so I get 2x greater than or equal to negative 7, which means x is greater than or equal to negative 7 halves. And then over here, subtract 3, I get 2x is less than or equal to 1, so x is less than or equal to 1 half. So on the number line, negative 7 halves would come first, and then 1 half would come somewhere else later on. And then we're going to be graphing OR here, right? So greater than negative 7 halves would be like this. Okay, see what's going to happen here? And then less than or equal to 1 half would be like this. And remember, these are ORs, so it's not an intersection of the two. It's just basically like what's going on, what's shaded. And it turns out the ORs on our boat ended up overlapping. We had an example like this in a previous lesson. So the interval is that literally everything is a solution. Negative infinity to infinity, all of it, the whole thing. Now, way at the beginning of the problem, I don't think I had to do any of that work because the question is, when will an absolute value be more than negative 4? And that answer is all the time because absolute values are always positive. I mean, at the very least, they'd be a 0. So when are they bigger than negative 4? The answer is all the time. So the special cases, if you recognize them, are actually awesome. So let's try to cheat a little bit here on part C. I first noticed that the bars are not isolated, so I need to isolate them by subtracting the 8, and I think I see what's going on. Absolute value of 4x minus 9 is supposed to be less than or equal to negative 3. Now don't jump the gun and say, oh, it's like the last problem. No, it's not. Because this time I'm asking you when will an absolute value problem come out to a number that is less than negative 3? And the answer to that is never. You will never get an absolute value problem coming out to less than -3 because they're always 0 or greater, always positive, So the interval solution or the graph solution or any of it is that there is no solution. So don't write 0 because 0 is a number. The words no solution is what I'm looking for. So if only I put stars around every question that was weird, that'd be nice. Part B, they're not isolated yet. Let's go ahead and isolate them. So if I add 4, my new problem, I'm going to cross that one out totally, is -x plus 5, absolute value bars around that, is greater than 10. When I go to set up my two problems, man, I've like done all ORs for some reason. -x plus 5 is greater than 10. The reason I know it's an OR is because the problem originally, after I isolated here, is a greater than. So -x plus 5, that does not change, but this changes, is now less than -10. So subtracting 5, you get -x greater than 5, so x, we're going to divide by -1 here, so we're going to flip the sign to a negative, less than -5. Or subtracting 5, so -x less than -15, same thing, I'm dividing by a negative, so I got to flip the sign, greater than 15. So here's -5, here's 15, greater than 15, less than -5, parentheses on both ORs, that's what an OR should look like, and the problem didn't have stars around it, so I knew it wouldn't be weird. All right, -infinity to -5, union, because there's a jump, 15 to infinity. Good times. So the idea here, solving absolute value equations, easy peasy lemon squeezy. Isolate the bars, set up your two equations. The second one is the negation of the answer. Watch for special cases. Absolute value inequality is a little more exciting because you have to, yes, isolate the bars, but then you have to decide if it's and or. Then you have to call back some knowledge about what that means, and then you have to remember how to solve inequalities. Good time. All right, best of luck.